This video is a practical demonstration of all the concepts we've covered in inference. There's nothing new, we just demonstrate confidence intervals and hypothesis tests for means and proportions based on the central limit theorem and a normal model. So let's start with the sample mean and estimating a confidence interval. We can first of all define our population parameter of interest. Often we use the Greek letter mu when it's a population mean. Our point estimate is the mean in the sample. We can call that x bar. We know that in repeated samples of sufficient size, as long as the distribution is not too skewed, then the sample mean will follow a normal distribution with a mean equal to the population mean and a standard deviation or standard error equal to the population standard deviation divided by the square root of the sample size. And because we don't know the population standard deviation, we estimate it using the sample standard deviation. So we can then use the normal approximation to estimate the confidence intervals for our point estimate. And this is a result of central limit theorem and is valid under particular conditions, namely that observations in the sample are independent, and as just mentioned, that the sample size is sufficiently large and the population distribution is not excessively skewed. Or this is perfectly okay to use the normal approximation if the underlying population distribution is normal. So in that case, the sample size is not so important. The confidence interval is then given by the point estimate minus z times the standard error, and the point estimate plus the z statistic by the standard error. And the values for z come from the standard normal distribution. For a 95% confidence interval, this is 1.96. And let's just introduce a bit of terminology here. Some people call this part the error factor, just because it represents the level of precision or amount of sampling error that we wish to bracket around our point estimate. And the formula here is the basic form for all confidence intervals that use normal theory. It's only the equation for the standard error that will change depending on the type of point estimate that it is. So this is a basic formula worth remembering, as it allows you to perform quick calculations and inference on the fly. So let's show an example. We want to know the mean birth weight in a population of babies conceived from IVF. We've got a random sample of 100 babies. The sample standard deviation is half a kilogram. A 95% confidence interval can then be calculated using the basic equation for a confidence interval just shown. And we get a 95% confidence interval of 3.1 to 3.298. So let's recap on interpreting confidence intervals. Here's a selection of interpretations of that confidence interval. Pause the video, have a read through, and decide which of these options is the best interpretation of that confidence interval. And then I'll go through them. So the first one, that's wrong. This refers to the sample. We know the average birth weight in the sample. We calculate that. The confidence interval attempts to tell us something about the population mean birth weight. B, the second one, that's correct. It refers to the average birth weight in the target population. And C is wrong. It refers to individuals in the population. The confidence interval is for the mean, not for individual observations. And likewise, D is wrong too. It mixes up a confidence interval with a 95% reference range. A reference range is for individual values in the population. It's calculated in exactly the same way as a confidence interval, except it uses a sample standard deviation, which is a descriptive measure of variation in the sample, instead of the standard error, which is an inferential statistic about the sampling variation of the point estimates. So next we can do a one-sample hypothesis test for the mean using normal theory. To do this, we first formulate the null hypothesis, and we can call that H0. And it's typically stated in this form. The population parameter is equal to the null value, and the null value comes from the null hypothesis. It's the value that it would take under the null hypothesis. We then calculate our estimate of the population parameter, our point estimate, and we can call that x bar again, as it's a sample mean. And we also need to make sure that our data meet the assumptions for valid inference using a normal approximation. And this is exactly the same as what we've been through before. We then calculate our test statistic, which is called Z, because we're using the standard normal distribution. This is calculated as a point estimate minus the hypothesized value for the population parameter, mu0, divided by the standard error. We then use a Z statistic to calculate a p-value and interpret and evaluate the hypothesis. So let's use the same example. We want to know whether babies born from IVF have the same birth weight as babies conceived naturally. We've got the random sample of 100 babies with a sample mean of 3.2 kilograms and a sample standard deviation of 0.5 kilograms. We know the population mean of babies conceived naturally. This is 3.32 kilograms. This is our hypothesized null value for the population parameter or mean birth weight in the entire population of IVF babies. Our null hypothesis is this, that the population mean birth weight among IVF babies is equal to 3.32, or the same as other babies conceived naturally. We've already shown the point estimate, which is the sample mean in IVF babies, 3.2 kilograms, and we can check the assumptions so that we can use this normal approximation, and they're all met, and then we calculate our Z test statistic. Again, remind ourselves that because we don't know the true standard deviation in the population, to calculate the standard error, we'll use a sample standard deviation in our group of IVF babies as an estimate of the population standard deviation. And our test statistic equals minus 2.1. Next, we work out a p-value. It can be helpful to see a picture of what we're doing when we do that. So here's the standard normal distribution. We've calculated a test statistic of minus 2.4 here. So we want to work out the area in the two tails beyond minus 2.4 and plus 2.4. And that area corresponds to the p-value for observing a difference as extreme as 2.4 standard errors away from the hypothesized null value. So this is a two-sided test. Notice my use of the words observing a difference as extreme, and also the way that the probabilities are summed in each tail of the distribution. And from either statistical tables or a computer program, we get a p-value of 0.016. So let's recap on interpretation. Here's a selection. Pause the video, read through and decide which you think is best. So hopefully you picked A, that's the correct one. And that follows our basic format for the interpretation of a p-value, that is, the probability of seeing a difference as big as we observed if the null hypothesis is true. So B, well, that's not technically wrong, although as we discussed in earlier videos, we prefer not to dichotomize p-values into either being significant or not significant when we report their results. We said that it's not really interpreting a p-value. A p-value is the strength of evidence against the null, so it should be interpreted in a more continuous way. And C is naturally wrong as well because the p-value is very low, so it's evident there, it's suggesting there is evidence against the null hypothesis. And lastly, D is wrong too. A p-value is not the probability that the hypothesis is true, it's the probability of seeing such extreme data given the null hypothesis is true. Let's talk about inference with a sample proportion. This will be much quicker as it's exactly the same as with a sample mean, except we're substituting a different type of point estimate and we're also using a different standard error. Again, we have the same logic as for a mean. Define the parameter of interest, and this time we call it pi. That's a Greek letter that tends to be used to denote a population proportion. And then we have our point estimate p, that's the proportion we observe in the sample. And we note that as long as the sample is of sufficient size, then our point estimates for the sample proportion in the long run will follow a normal distribution with a mean that's equal to the population proportion and a standard error given by this equation. And we use these guidelines here to work out whether the sample is of a sufficient size or not for that approximation. And we can use the normal distribution to work out our confidence intervals. This is exactly the same as outlined before for the sample mean. The only difference is the assumption here regarding the sample size, so I won't talk all the way through this again. Here's an example. So now, instead of looking at the mean birth weight among IVF babies, let's look at the proportion of low birth weight babies, those born less than 2.5 kilograms. So using the same random sample of 100 babies from mothers that conceived from IVF, we get a proportion of low birth weight babies of 0.12 or 12%. We can use our equation for the standard error, as our sample size is large enough for the normal approximation. And when we plug values into this equation here, we get a 95% confidence interval of 0.056 to 0.18. So how can we interpret that? Well, we can say we're 95% confident that the true proportion of low birth weight babies born to mothers that have undergone IVF lies somewhere between 0.056 and 0.18, or 5.6 and 18%. We can also do a one-sample hypothesis test for a proportion using normal theory too. And to do that, we go through the following steps. These are essentially the same as for a sample mean, except for one slight difference, and that relates to the standard error. We know that the standard error of a proportion is different to the sample mean, but it's also slightly different for a hypothesis test in another way too. You might remember that the standard error for a proportion depends on the size of the proportion. We saw that in the video on central limit theorem. Hence, because we calculate the p-value under the null hypothesis, we estimate the standard error under the null hypothesis too, or the standard error when pi is equal to our hypothesis null value, and that's denoted by pi 0 here. So let's use the same example. We want to know if the proportion of low birth weight babies born from IVF is different to babies conceived naturally. So we've got a random sample of 100 babies, and the proportion of low birth weight in this sample was 0.12 or 12%. We know that the low birth weight proportion among babies conceived naturally is 0.07 or 7%. So this is our hypothesized null value that we will test against. Our null hypothesis is this then, that among IVF babies, the proportion of low birth weight babies is equal to 0.07. In the sample we collected, the point estimate was actually 0.12. We can also then check the assumptions that we need in order to use the normal approximation, and they all seem met. Therefore, we'll go ahead and do our test using the Z distribution. We then calculate our test statistic using the equation we showed before, and we get a test statistic, or a Z statistic, equal to 1.92. Next, we calculate a p-value, and it's exactly the same as for a sample mean. So our test statistic was 1.92, so the two-sided p-value is the error in the two tails beyond plus or minus 1.92. And from either statistical tables or a computer program, we get a p-value of 0.054. So we conclude that there's some evidence that the proportion of low birth weight babies differs among those babies conceived from IVF, although the evidence is weak. So as well as reinforcing the basic structure and principles of confidence intervals and hypothesis tests through some examples, there are a couple of other key learning points from this video. And they are, firstly, that the concepts underlying a confidence interval and hypothesis test remain the same regardless of the type of point estimate. And secondly, that the structure and procedures are also broadly similar regardless of the type of point estimate. It is only really the standard error that changes. So there were no new terms introduced in this video.